This is my Module 3 Business Analytics presentation on queuing at the supermarket. Imagine a supermarket. Here is one of its cashiers. The interaction we're going to look closely at is queuing. When customers are done shopping, they come to the cashier to check out. We are given that the customers arrive on average in intervals of 12 seconds, take 15 minutes to shop, and on average take 4 minutes to check out with a cashier. Thus, they have to wait before their turn in line, and therefore the queue will be a dynamical system we can observe. I started with modeling 1 to 20 cashiers and some number of customers. I found that the more customers I had, the more overall time customers had to spend in the market. In this graph, top to bottom is 1 to 20 cashiers. From this, we can see that when there are less or equal to 20 cashiers, as the number of customers increases, the total average time increases as well. An increased number of cashiers reduces this rate of increase. Then I observed the case where the number of cashiers is greater than 20. Notice the difference in scale. The highest number is 19.3 and the lowest is 18.7. This was a very big change. From this we can see that when the number of cashiers is greater than 20, the previous pattern is thrown out the window, and there are only slight deviations from the 15 minutes of shopping time plus 4 minutes of average checkout time equals 19 minutes. These fluctuations are largely determined by random noise. The average time starts to go up slightly only when the number of customers grows very large. I also looked at what the distribution of the total times of each customer looks like in a histogram. In a histogram, each bar shows how many customers' total market time fit within a bin that is marked by the x-axis. For example, if I wanted to see around how many people spent close to 100 minutes in the supermarket, I can look at the x-axis and find 100 and then see how many customers fit in that bin by looking at the y-axis, around 650 people. Remember that since we are running 1,000 simulations of 100 customers, this number is out of 100,000. Here are the ones with less or equal to 20 cashiers. We can see that when the number of cashiers is less or equal to 20, we get this spike and a bump at the end. The spike is from the first customers arriving into an empty queue. Those customers don't have to wait in any queue because they are the first ones in the supermarket. Thus, their market time is around 90 minutes, as explained before, with some noise. As more people come, the waiting time in the queue rises, which means that it doesn't stay within a range and increases exponentially. This process is random, and we use many iterations to combat this randomness. This results in a distribution that is shown by the bump. Here are the ones with more than 20 cashiers. When there are more than 20 cashiers, the spike is still present, but the bump is smoothed out dramatically. This is because, on average, customers will arrive in intervals of 12 seconds. So the 21st person will come in 4 minutes, and by then, the first cashier will be done helping their customer and will be available. However, this is all assuming that all interactions are equal to their average time, which, of course, is not true. Thus, the noise causes customers to wait in queue, resulting in more total time spent in the market. Plotting them together on the same scale shows how the initial spike and bump are seen in all of the graphs, and as you increase the number of cashiers, the spike gets steeper and the bump gets smaller and smaller. Plotting them on a log scale shows how the initial decrease spikes all have very similar exponential slopes, and the ending exponential slope gets more and more negative the more cashiers you have. Thanks for listening.